Hello students, good time to all. I am Chandan Kumar Pradhan. Welcome to the YouTube channel Chandan Physics. In this video, we are going to discuss barrier potential and barrier width. Let's begin. To calculate barrier potential and barrier width mathematically, we have to consider a step graded PN junction. P type semiconductor, N type semiconductor, and the doping concentration used throughout that of P type and N type are almost constant throughout that of junction. In that of PN junction, that be the depletion region, and which is also called as the barrier width. The potential developed throughout that of barrier is known as barrier potential. Let we take it from the graph. If we plot a graph in between distance to that of volume charge density, that region let for P type, that region let for N type. So, the width of that of barrier from x2 to x1 in N region, that is at x1, that of P region it is minus x2, and in that of N region the density of donor atom, that is Nd, charge of electron, density of donor atom N of T. Similarly, in that of P region, that is the density of acceptor atom minus E N A acceptor atom, that is the positive region, that one is the negative region. According to Poisson's equation, d square V by dx square is equal to minus rho x divided by epsilon, where V, that is the electric potential, rho of x volume charge density, at a distance x from that of a junction, rho of x, at a distance x from the junction and epsilon permittivity of semiconductor, permittivity of semiconductor. By using that expression for Poisson's equation, in n region of a depletion layer, that is the graphical view of space charge density in the step junction. In n region of depletion layer, that depletion layer from 0 to x1, we use that Poisson's equation d square v dx square is equal to, here volume charge density E n d, so negative sign, E n of d divided by epsilon, or d by dx of dv by dx is equal to minus E n d divided by epsilon, or d of dv by dx is equal to minus E n d divided by epsilon dx. Integrating both sides, so integration over d of dv by dx is equal to minus integration over E n d divided by epsilon dx, or this dv by dx is equal to this integration minus E n d x divided by epsilon plus C1, where C1 the constant of integration. Let me take it as equation number 1, and C1 that is the constant of integration. In same way, we can apply that expression for P region of that depletion layer. In the P region depletion layer, again in P region of depletion layer, that region from minus x2 to 0, minus x2 up to 0, d square v by dx square is equal to minus e here it is minus e n a minus minus plus, so plus e n a divided by epsilon, or it is d by dx of dv by dx is equal to e n a divided by epsilon, or d of dv by dx is equal to e n a divided by epsilon dx. Integrating both sides, the integration over d of dv by dx is equal to integration over e n a by epsilon dx. We have the result. So, dv by dx is equal to e n a divided by epsilon x plus c2, that is the constant of integration, Now, we can evaluate what be the constant of integration c1 and c2 by applying the boundary conditions. So, the boundary conditions, the potential is uniform at the boundaries, means at x is equal to plus x1 and x is equal to minus x2, that potential dv by dx will be 0 as it is uniform. Therefore, this change with respect to distance as 0. At boundary condition, at x is equal to x1 and x is equal to minus of x2, the potential is uniform. Therefore, rate of potential with that of distance is equal to 0. That boundary condition is applied to equation number 1 and equation number 2 in order to evaluate c1 and c2, the constant of integrations. Now, equation number 1 becomes, equation number 1 becomes dv by dx is equal to 0. So, 0 is equal to minus e n dx divided by epsilon plus c1. Here we put x is equal to plus x1. From this C1 is equal to E ND divided by epsilon. Now one constant C1 is evaluated. Next, equation 2 becomes equation 2 as dv by dx as 0 is equal to that quantity. 0 is equal to as we put x is equal to minus of x2, therefore it is minus E n a here it is x1, x as x1, x as x1 minus E n a x2 divided by epsilon plus C2. Here we use x is equal to minus x2, x is equal to minus x2. Another constant C2 as E n a x2 divided by epsilon. These two constant of integrations are now evaluated, but we know the relation between electric field and potential. Electric field is a negative of potential gradient. As electric field is defined as the negative of potential gradient. Therefore, for n reason E n of x is equal to minus dv by dx. The value of dv by dx now we have to put from taking n region expression. This is the expression for n region dv by dx. Or that is for n region. So, n region dv by dx is put it n of x is equal to E n dx divided by epsilon minus C1, or E n of x is equal to E n dx by epsilon value of C1 minus E n d x1 divided by epsilon, or E n of x is equal to E n d divided by epsilon as common inside that bracket x minus x1. Similarly, for p region E p of x is equal to minus dv by dx, that for p region. Therefore, dv by dx expression from p region is put it here E p of x is equal to minus E n a x divided by epsilon plus minus C2, or E p of x is equal to minus E n a x divided by epsilon, then the value of C2 is put, that is minus E n a x2 divided by epsilon, and the value of C2. Therefore, E p of x is equal to minus E n a by epsilon x plus x2. We take it as equation number 3, that one as equation number 4. Electric field for n region, electric field for p region. Now, the expression for potential can be calculated by taking that of electric field. The potential in the n region, that is V n of x potential integration n of x dx, as we use the relation electric field is the negative of potential gradient E is equal to minus dV by dx. Therefore, that potential is calculated as integration over electric field dx. The value of E n of x is put for n region. Is equal to value of E n of x minus integration over E n d divided by epsilon x minus x1 dx. And for V n of x, or V n of x, evaluating that integration E n d x square divided by 2 epsilon integration of x dx as x square by 2 minus minus plus E n d x1, then integration of dx as x divided by epsilon, let C3 the constant of integration. Equation number 5, where C3, that is the constant of integration. Similarly, the potential in the p region, the potential in the p region, V p of x negative integration over E p of x dx. The value of E p of x dx is put. Therefore, V p of x is equal to minus minus plus integration over value of E p of x as E n a divided by epsilon x plus x2 dx. Now, evaluating that integral, so V p of x is equal to E n a x square divided by 2 epsilon plus E n a x2 x divided by epsilon plus C4, at equation number 6, where C4 that is the constant of integration. Now, the constant of integration C3 and C4 can be evaluated by taking proper boundary condition. Now, using proper boundary condition, we can easily calculate the integration constant C3 and C4. Using boundary conditions, at x is equal to plus x1, v of x is equal to v of b, whereas v of b, that is the barrier potential. And at x is equal to minus x2, that potential is 0. Okay. So, equation 5 and 6 change to, we put that proper boundary conditions. Therefore, equation 5 becomes Vb is equal to minus E n d x1 square divided by 2 epsilon plus E n d x1 square divided by epsilon plus C3. Use that boundary condition as x is equal to x1, Vx is equal to Vb. That for n relation, or Vb is equal to E n d x1 square divided by 2 epsilon plus C3, or C3 is equal to Vb minus E n d x1 square divided by 2 epsilon. So, constant C3 is evaluated. Now, we put that C3 in equation number 5. Therefore, V n of x is equal to minus E n d x square divided by 2 epsilon plus E n d x1 x divided by epsilon minus E n d x1 square divided by 2 epsilon plus Vb. The value of C3 is put here, or Vn of x is equal to minus E n d divided by epsilon as common in the bracket term, that is x square divided by 2 plus x1 square divided by 2 minus x1 into x plus Vb. Equation number 7. Again, equation number 6 becomes, we use the boundary condition as for p type at p region x is equal to x2. So, v of x will be 0. Now, equation number 6 change to zero is equal to E Na x2 square divided by 2 epsilon minus E Na x2 square divided by epsilon plus the constant C4, or 0 is equal to minus E Na x2 square divided by 2 epsilon 1 by 2 minus 1, that is minus half, plus C4, or C4 is equal to E Na x2 square divided by 2 epsilon. Therefore, that equation number 6 change to V P of x is equal to E Na x square divided by 2 epsilon plus E Na x2 x divided by epsilon plus E Na x2 square divided by 2 epsilon. The value of C4 here we put. Therefore, V P of x is equal to E Na by epsilon as common. In the first term it is x square by 2 plus in the last term, that is x2 square divided by 2. From that term it is x2 into x. That is equation number 8. Now, equation number 7 and equation number 8 on the basis of the constant C3 and the constant C4 we evaluate. Since the electric potential is continuous at x is equal to 0, hence that potential at n region is same as that potential in that of p region at x is equal to 0. Therefore, Vn at 0 is same as Vp at 0. The value of Vn when x is equal to 0. So, that expression 7 changes to minus E Nd x1 square divided by 2 epsilon plus Vb, as we put x as 0 is equal to again V of p when x is equal to 0, that equation 8 changes to E Na x2 square divided by 2 epsilon, or V of b is equal to E Na x2 square divided by 2 epsilon plus E Nd x1 square divided by 2 epsilon. Now, taking E divided by 2 epsilon as common, Na x2 square plus Nd x1 square in that of bracket term, that will be the required expression for barrier potential. This is the expression barrier potential, or that is the junction potential of a step junction, step graded junction. expression from barrier potential or junction potential of a step junction. From that expression, we can also evaluate the barrier width. As we know from charge conservation, n d x1 is equal to n a x2. Therefore, x1 by x2 is equal to n a by n d, or x1 square by x2 square is equal to n a square by n d square. Again, x2 by x1 is equal to n d by n a, or x2 square by x1 square is equal to n d square divided by n a square. These two expressions we can use by transferring that equation number 9. From equation number 9, we have V of B is equal to E by 2 epsilon 1 plus N A x2 square divided by n d x1 square whole into n d x1 square. Here I divide n d x1 square and multiply n d x1 square. Okay. So, V of B is equal to E divided by 2 epsilon 1 plus N A by N D. Here x2 square divided by x1 square, x2 square divided by x1 square, that is n d square divided by n a square, n d square divided by n a square whole into n d x1 square using equation II, or V of B is equal to E by 2 epsilon 1 plus under cancellation n d divided by n a whole into n d x1 square, or V of B is equal to E by 2 epsilon taking LCM n a plus n d divided by n a whole into n d x1 square. So, x1 square will be 2 epsilon n a v b divided by E whole into n a plus n d whole into nd. From this x1 can be calculated. So, x1 is equal to its under root 2 epsilon na Vb divided by E whole into Na plus Nd whole into Nd under root. Taking equation number as 10. Again using the same equation, using equation number 10, sorry, equation number 9, we have that equation number 9 further written as by dividing n a x2 square and multiplying n a x2 square. So, V of b is equal to E by 2 epsilon 1 plus Nd x1 square divided by Na x2 square whole into Na x2 square, or V of b is equal to E by 2 epsilon 1 plus Nd by Na into, in place of x1 square divided by x2 square, x1 square divided by x2 square, using equation number 1 we have Na square divided by Nd square Na x2 square, using equation number I is equal to, or V of b is equal to E by 2 epsilon 1 plus Na by Nd whole into Na x2 square, or V of b is equal to E by 2 epsilon, taking LCM, Nd plus Na divided by Nd Na x2 square, or x2 square is equal to 2 epsilon Nd Na Nd Vb Nd Vb divided by E whole into Na plus Nd whole into Na. Then x2 square is equal to its under root, or x2 square is equal to 2 epsilon Nd V of b divided by E Na plus Nd whole into Na under root. That is equation number 11. Now we can use equation number 10 and 11 in order to calculate the barrier width. At the barrier width, therefore barrier width W is equal to x1 plus x2. From that of figure, look here, that is the barrier width, here x1, here x2. So, x1 plus x2 is the barrier width. Now the value of x1 from equation number 10 and value of x2 from equation number 11 is put at with W is equal to 2 epsilon Na Vb divided by E Na plus Nd whole into Nd under root plus 2 epsilon Nd Vb divided by E Na plus Nd whole into Na under root. From equation number 10 and equation number 11 the values are put at W is equal to, taking the LCM E Na plus Nd Na Nd under root. First term it is 2 epsilon Na square Vb under root plus second term it is 2 epsilon Nd square Vb under root, or W is equal to 2 epsilon Vb under root as common, it is Na plus Nd divided by E Na plus Nd Na Nd under root, or W is equal to 2 epsilon Vb 1 under root to that term we obtain under root of Na plus Nd divided by E Na Nd under root. Therefore, W is equal to 2 epsilon Vb Na plus Nd divided by E Na Nd whole under root. So, that is the required expression from barrier width. This is the expression barrier width or depletion width of a step junction. Barrier width or depletion width of a step junction. So, here with the help of this video lecture you understand the concept of barrier potential and barrier width. For N region depletion layer we use that expression. Next, for P region C1 and C2 is evaluated by taking the boundary condition C1 C2, then electric field is defined as the negative of potential gradient. So, electric field at N region and electric field at P region, by using that expression the potential in N region and potential in P region is calculated. Again the value of C3 and C4 is evaluated by taking the boundary condition. So, C3 is evaluated, then the value of C3 is put at next value of C4 is evaluated, then the value of C4 is putted, and using that expression at x is equal to 0, Vn of x is equal to Vp of x at x is equal to 0. So, the expression for Vb, that is the barrier potential or junction potential of a step junction. Next, barrier width is calculated by using the concept of charge conservation. So, charge conservation concept used, we obtain two types of equation, and that expression for barrier potential can be changed by using that equation number 2, and we obtain the value of x1. Similarly, the value of x2 is evaluated, and finally, putting the value of x1 and x2, the barrier width is calculated. That will be the mathematical expression for barrier width or depletion width of step junction. So, with this useful and informative notes, let me wind up this session. Thank you.